There are two ways making matrix using AMOLED, which is AM AMOLED and PM AMOLED. The AM AMOLED is active matrix AMOLED, which consisted with 3 transistor and 1 photodiode cell. And passive matrix AMOLED is consisted with a 1 diode and 1 cell. The PM diode is cheaper because it consisted with only 1 cell. However, it has low latency, so uh, nowadays we use active matrix. The benefit using active matrix is that uh, it can be there is a capacitor, store capacitors, so it can buffer between the scan duration. So the TFT, the thin film transistors, which is peripheral to the AMOLED, there are 3 types. First of all, the alpha semiconductor. It is first developed and it has a state between the polycrystal and amorphous. It's basically amorphous, so it has lower mobility. And there is LTPS, which has higher mobility, but it needed to be a high temperature process, so it is hard to make and the yield is not good. So after that, the EXO was developed, which has relatively low mobility for ATPS, but it has lower temperature process. So, and there is a laser which uses a population inversion mechanism, which means that to make more carriers excited through the same time. So we call this a pumping the carrier. To pump the carriers, there are a lot of methods. For example, the chemical, gas, or uh, electric potential, or optical excitations. So the 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 mechanism of laser is that there is a lighting or light emitting diode, and we pump the excited electrons or carriers using various methods. So when the excited carriers when the carrier is excited, then the carrier would uh, vibrate. Carrier would move through this the lattice, and then the light would be emitted. So then when the light reaches to the OC, which reflects selectively, it is basically a mirror. So then the light flux would reflected to the highly reflected mirror. So after through these highly reflective mirrors, it reflects total light flux. So like avalanche effect, the light flux excites the carriers between the light emitting diode. So the F, so the light flux would be polarized. So the laser would be come out. And there is a laser diode which is not using pumping method. It uses a degeneratively doped silicons to make more carriers, and to be carriers to be stayed in the barriers, the PN junctions, we use the conformal structures to trap those carriers and uh, make more lifetime through in junctions. And there is CCD and CIS. The CCD means that charge coupled device that it it sensors light using this charge, So it is slow, but it has good sensitivity. However, the CIS, the CMOS image sensors, uses a voltage difference on most using this characteristic with MOSFET. It is fast, but less sensitivity than CCD. However, there is another advantages for the CIS, which is it is easy to make because it is a CMOS. Also, it can be more integrated than the CCD. And there is memories. The memories has a lot of varieties. In these sessions, we're gonna look out the SRAM and DRAM and flash memories. The SRAM means that static random access memory. The meaning of random access is not really randomic, but it means that it's not stack or queue, which means if you want the if you want the specific block, then you can get it out with the write and read at the same time, same duration. So the SRAM is non-volatile. So uh, it is not it it is it needs to not be refreshed. So the SRAM has low power dissipation of advantages, but however, it is very expensive and the SRAM cannot be relatively not be integrated than DRAM because the SRAM is consisted with 6 transistors in one cell, and the DRAM, which means a dynamic RAM, it is volatile memory, so it needs to be refreshed with durations of microseconds. So the this because of this disadvantage, the DRAM has higher power dissipations, and it has the more slower response time because DRAM is consisted with one transistor with one capacitor. Using these capacitors cell by cell, so by following the the decay time with tau equals R product the capacitance. So the DRAM is more slower than the SRAM. However, the DRAM is more faster, 10 times, 1,000 times faster than the flash memory. So flash memories, basically it uses a floating gate structures, which means the base typical most structures, there is a gate. However, in flash, there is a floating gate between the most structure. So how do we write and read on the flash memory? The flash memory uses the carrier to be injected between the gate and body in floating gate. So by reading, how By injecting electrons using this hot carrier effect and tunneling effect, which is Fowler-Nordenheim tunneling. So the threshold voltage, if carriers, let's say the carrier is electrons, if electrons trapped between in the floating gate, then the overall threshold voltage would be go higher, which means shifted to right on the IDVG curve. So using these techniques, we can define 0 and 1 through this how currents flows between the gate source and drain. So there is a lot of varieties in flash memory. There is SLC, the single level device. And there is a multi-level cells, which is, and there is 3-level cells. First of all, the single level cells is consisted with a one state, which can be stored in one cell, 0 or 1 state. And there is multi-level cells. It has a 2 state on the one device, so which can store 2 bits in the one cell. So which means that in SLC, the original threshold voltage, and there is another, the threshold voltage if the charge is trapped. So using this difference between current flows, we can define this cell has 0 or 1. In multi-level or 3-level cells, the threshold voltage is in here. There is 4 different threshold voltage, and there is 8 threshold voltage here. So the lifetime, the durability is has the most, that single level has most durabilities, and MLC and TLC. The reason SLC is most durable is that it has there's only 2 state, so there is a lot of noise margins between the states. So, and there is the difficulty of using this floating gate, because the mechanism to store or inject carriers in the floating gate was the hot carrier effect, which is it breaks down if it breaks down the oxide lattice, because oxide lattice or semiconductor lattice, because the hot carriers has a lot of energy, so it breaks the lattice through traveling through the lattice. So there is another structure called Sonos. The Sonos has the body, the silicon, and the oxide, tunneling oxide, and there is nitrate between the gate oxide. So the charges are stored in nitrate. The benefits using these Sonos structures is that it needs low power, because the Sonos layer is very thin, and by using these benefits, also we can make highly integrated and due to high K material, it has long retentions, and there is a also it can minimize this another disturbance. And like FinFET or Gate-All-Around nanowire, the trends also same for the for NAND flash, which uses a 3D structures. It can be more integrated, and there is NAND flash and NOR flash. The difference between NAND flash and NOR flash is that NANDs are page read, and the NOR flash can read cell by cell. So to reading time of NAND is slower than the NOR flash, but the integrations or density is larger than the NOR flash. So nowadays we use NAND flash because of this highly density. So, and there is a varieties of random access memories. First of all, the RAM or memory store. It uses high K materials to change resistance, and there is MRAM, which uses magnetic materials to change the resistance between two electrodes. MRAM and RRAMs has two electrodes, so it can be more integrated by the 3 electrode transistors.